Welcome to my video course on Communications-Based Train Control CBTC. I'm so thrilled to have you here with me. Today we're really going to move past the basics and completely unpack the vital engineering, the dynamic architecture, and the high-capacity technology that quite literally makes modern mass transit possible. Let's dive right in.
So here's our roadmap for this session. We'll be covering the evolution of rail signaling, defining what CBTC actually is, looking at moving blocks versus fixed blocks, and breaking down the core CBTC architecture. Then we'll get into real-world migration strategies and wrap things up with the future and cybersecurity of these networks. All right, Section 1, the evolution of rail signaling. Let's set the stage and establish a little historical context so we can really appreciate the engineering problem that CBTC actually solves. Urban rail signaling has a really rich 150-year history. If we look back at the 1870s, systems relied on purely mechanical interlockings. We're talking literal, pneumatically powered, physical levers and switches. Fast forward to the mid-1900s, and the industry evolved to use track circuits and axle counters. These are basically hardwired electrical systems that detected whenever a train's metal wheels bridged a physical gap in the track. By the 1990s, we finally saw the introduction of automatic train operation. But today, the absolute pinnacle of this evolution is the transition to fully wireless, continuous communications networks.
Now, you might be wondering, what was actually wrong with those older systems? Well, the core problem is something called the absolute block system. Traditionally, railway tracks are divided up into rigid fixed-length segments called blocks, and the golden rule is that only one train can be in a given block at any time. Because these blocks are completely static and they're built to accommodate the absolute worst-case braking distance of the fastest train on the line, they leave massive amounts of unutilized empty space between the trains. You simply can't safely fit more trains onto the track, which severely limits the capacity of a growing city's transit system. It's incredibly inefficient.
Moving on to Section 2, defining CBTC. Let's look at the technological paradigm shift that was required to actually fit more trains onto that exact same track.
And that brings us to the formal definition of communications-based train control, or as the IEEE 1474 standard puts it, it's a continuous automatic train control system utilizing high-resolution train location determination that is completely independent from physical track circuits. Instead, it relies on continuous, high-capacity, bidirectional data communications between the train and the wayside equipment. So, what's the big takeaway here? It's the severing of the physical wire. We are fundamentally moving from tracks detecting trains to trains actively communicating their precise location over radio waves.
Section 3, moving blocks versus fixed blocks. This shift to dynamic safety distances unlocks what is arguably the most important operational concept in modern rail today. Under the old fixed block system we talked about, the safety distance is the static, rigid boundary enforced by heavy track hardware. But under CBTC's moving block system, that safety distance is calculated in real time. It's based on the train's exact speed, its direction, and its braking capability at that exact millisecond. If a train is moving fast, the safety buffer in front of it is long, but as that train slows down to approach a station, that safety distance dynamically shrinks. This real-time calculation is the secret sauce. It's what allows trains to safely run much closer together, unlocking incredible frequencies and headways as short as 90 seconds.
Let's dive into Section 4, core CBTC architecture. We know the theory now, so let's break down how engineers actually build this system.
The whole CBTC architecture is built on an interconnected triad. You basically have three vital components. First, there's the train-borne system sitting right on the vehicle itself. Second, the wayside system located along the physical tracks. And third, binding all of this together is the data communication system, or DCS, working alongside the automatic train supervision network up at the top level. The DCS is the backbone here. It ensures that critical, life-saving data packets are transmitted between the moving train and the trackside instantly without fail.
So, let's look at the continuous, real-time loop that keeps everything moving safely. Step 1. The train detects its exact location by reading passive transponder tags that are physically placed on the track every few hundred meters. Step 2. The train's onboard computer wirelessly transmits this precise position along with its current speed to the wayside zone controller. Step 3. That zone controller looks at all the trains in its specific area and generates a safe movement authority, which is basically a strict limit of how far and how fast the train is allowed to go. Finally, step 4, that movement authority is transmitted right back to the train. And this entire loop, it happens multiple times every single second.
Now, meanwhile, overseeing all of these localized zones is the operational control center,
This is where the Automatic Train Supervision, or ATS, operates. The operators sitting here aren't actually driving the trains with a joystick. Instead, the ATS issues high-level route driving plans to the various trackside controllers over a massive fiber optic backbone. They are constantly monitoring the entire flow of the network, adjusting the schedules, and making sure the automated system is running smoothly.
But we have to deal with reality here. As literally any engineer will tell you, radio communication, just like the Wi-Fi in your house, is inherently unreliable. Data packets get delayed, handovers between access points can drop, and signal interference definitely happens. Because CBTC completely relies on this radio link to know exactly where the trains are, systems require really strict protection margins built right into their braking calculations. Basically, if communication is lost, the train immediately assumes the absolute worst and triggers an emergency brake protocol. Furthermore, these networks almost always maintain a secondary, conventional fixed-block interlocking system as a fallback. That ensures if the wireless network goes completely down, the railway can still operate, just at a much lower capacity.
Section 5. Real-world migration strategies. Upgrading live, functioning railways without shutting down a major city is, quite frankly, an absolute engineering nightmare.
Just think about a legacy system like the London Underground for a second. You are dealing with 150-year-old infrastructure, ancient mechanical relays, and literally millions of daily passengers. You absolutely cannot just turn off the railway for 6 months to install a bunch of new Wi-Fi routers. The rolling stock has to be carefully managed. To make this work, existing trains have to be retrofitted to be dual-fitted, meaning they carry both the old mechanical Tripcox signaling equipment and the shiny new CBTC onboard computers.
The industry standard to handle this incredibly complex process is a highly cautious, 4-step cutover strategy. First, extensive installation and testing happen completely off-site on dedicated test tracks. Second, engineers use simulated virtual test trains to test the new software against the line's unique track geometry. Third, they run actual ghost trains during those incredibly brief 3 to 4 hour engineering windows in the dead of the night, safely switching control back to the legacy system right before the morning commute starts. Finally, once reliability is undeniably proven, a specific zone is fully commissioned. The area is officially cut over to CBTC, and only then is the legacy equipment unbolted from the floor and decommissioned for good.
And finally, Section 6, the future and cybersecurity. Securing wireless trains introduces incredible efficiency, but it also brings modern vulnerabilities to the table.
I want you to really think about this for a second. What happens when the system governing a multi-ton metal vehicle full of passengers is no longer a closed physical circuit, but an invisible data stream traveling through the air?
The reality is the cyber threat. 20 years ago, signal engineers could confidently say their systems were entirely isolated from the outside world. Today, a train is basically a flying IT network. They're connected to passenger Wi-Fi, CCTV cameras, public address systems, and software updates are often loaded right on the train via portable media like USB drives. The signaling system is no longer naturally immune to hackers. Modern railway engineering now demands that signal engineers also be highly skilled cybersecurity experts. They have to implement strict firewalls, deep packet inspection, and rigorous safety by design principles just to defend these critical public assets.
And the technology isn't slowing down anytime soon. Looking out on the horizon, we are seeing the integration of ultra-reliable 5G mobile networks replacing standard Wi-Fi, providing way lower latency and even tighter train headways. The Internet of Things is going to allow for predictive maintenance, where track sensors report their own wear and tear directly to the control center automatically. All of this is pushing us rapidly toward a reality of fully autonomous driverless train networks operating completely safely beneath our feet.
CBTC really is a brilliant blend of mechanical engineering, radio physics, and advanced software design, all working together in perfect, vital harmony. But as we hand over complete control of these massive networks to autonomous algorithms and invisible wireless data, we have to ask ourselves, are we fully prepared for the day the network goes dark? Thanks, we can see you in next